Good evening to one and all. Am I audible? Good evening all. Am I audible?
Yes, sir. Audible.
Yes, sir. Perfectly audible.
Good evening all. Respected Kulkarni sir, IAPT national officials, and all the other dignitaries and all the participants. Warm good evening once again. Today's speaker is Mr. N. Kiran from Karnataka. Welcome, sir.
Good evening, sir. Good evening.
Good evening, sir. Dr. Vandana will host today's proceeding without wasting much time. I will hand over the proceedings to Professor Vandana Luthra, ma'am. Vandana, ma'am, please take care of today's.
Yes, thank you. Thank you so much, Dr. Madhusudan. Am I audible?
Yes, ma'am. You're audible.
Okay. Yes, thank you so much. A very pleasant evening to everyone in this 8th session. We welcome Dr. Kiran here and
Thank you,
greetings to Dr. Kulkarni, President
Yes.
IAPT, seniors from IAPT, resource persons, observers, volunteers, and our enthusiastic participants. We appreciate your keen interest of all of you. And today we are going to have another exciting session, which is a continuation of a session tomorrow, which we had by Dr. Kiran. And today is the 8th session on quantum teleportation. So important announcements to make. Keep the mics muted. You may unmute in question and answer session after the questions asked in the chat are addressed. And please raise your hand if you wish to ask any question. Secondly, questions can be posted in the chat. If your question is not answered, please send us on email as well. All are requested not to scribble on the screen. Again, this is a humble request to all of you. And all are requested to join the WhatsApp group, but I hope 1 or 2 people are still left. They can still join. 80% attendance is mandatory, as well as participation in the quiz for getting a e-certificate. And we are sharing, emailing all the relevant material in the group. And please join only with your registered email ID. There is one email ID, one joining from a number 12022, and there is another person who is joining from Redmi. So please change your name so that we can get to know that who is actually attending it. So today we have a wonderful speaker, which we had a talk yesterday on quantum entanglement. And today we are going to have a continuation of that talk as quantum teleportation. So let us welcome Dr. Kiran N, who is a lecturer in PU College, Karnataka. He holds a master's degree in theoretical physics, focusing on quantum field theory with a strong academic foundation. He specializes in teaching physics to students K11 and K12 for board and competitive levels. His lessons are tailored to individual needs, making complex concepts understandable and engaging. And we saw a demonstration of that yesterday. He brings real life applications into teaching, aiming to inspire curiosity and critical thinking. He has a total of 9 years of experience, which includes 5 years in research, operation of HRTEM at Bengaluru Icon Analytical Private Limited, IOP Bhubaneswar, and he has got 4 years of experience in academics. So we welcome you, Dr. Kiran, and looking forward to your wonderful talk.
Yeah,
Over to you now.
Thank you, ma'am. Thank you for giving me a wonderful introduction about me. So good evening to each and everyone. So
Good morning,
good morning, sir. Since sir is in far away. Okay, good morning, sir. So good morning, Kulkarni sir, and also Madhusudan sir, Rajesh sir, Vandana ma'am, and all the IAPT members, and also all to my dear students. Okay, so we are going to discuss in today's class the continuation part of this yesterday class, which we were discussing mainly regarding the quantum entanglement. So I hope that you have been cleared with my talk regarding yesterday's. Now I'm going to talk regarding the quantum circuit, which was the last concept of the quantum entanglement. That Bell state or entangled state is one of the most important property for today's class also. Okay. So I'm going to just brush up whatever we have discussed. So in yesterday's class, we were looked over what is meant by the tensor product. So how to do the operations of the tensor product. Then we have also represented both the basis states of the multiple qubits, that is the 2-qubit system. Then we have also represented the basis states and how to do the operation of the basis states by using the tensor product. Then we got some of the results, and you also done, lot of students has answered almost all the questions. So then we also represented in terms of an identity matrix. Then along with that, we also go and look over what is the equivalent gate for the 2-qubit system. That is nothing but a controlled NOT gate. So which is one of the most important gate for the 2-qubit system, and which is very equivalent to the XOR gate. We also looked over the XOR gate circuit representation truth table, and also the comparison of the CNOT gate by doing again the operations. So CNOT gate, we also looked over what is the circuit representation, matrix representations, and what is the most important thing. This is very, very important. So whatever we have discussed, this one minute, I'm going to show that in the laser pointer. Okay, this one. So this, whatever it is in the box, it is very important. I hope that it's been clear to you. So wherever I come, I'm going to use that again. The same box I will take. I will show you there also. Okay, even in today's class. And we have done some operations mainly on CNOT basis states. We came to know what is the truth table, which is very identical with the XOR gate. Now, in today's class, we are going to perform another very, very important concept, which we are going to come to the Bell state or the entangled state. So through this CNOT gate, we are going to represent through the quantum circuit. So what is that quantum circuit here? See, the CNOT gate, whatever we have represented, we have taken the Hadamard gate to the controlled bit. Okay, so this is the control stage, this is the target bit, this is the controlled one. So here I am going to take the state as KET0 and KET0, this for control and also for the target. Now, this is the representation of the initial state, which I am going to represent it by the phi xi function. Okay, so this is KET0 tensor product with the KET0. And this is the representation of the same thing in an easier manner. Okay, then what is the output of this one? How to calculate this one? This is very, very important. Okay, so here the output wave function represent. First, we need to take the CNOT gate. After that, I need to do the tensor product of this Hadamard gate with the identity matrix. So we know 2 cross 2 identity matrix 1 0 0 1. We will do that one now. Okay, and I need to take that one with the xi initial state, whatever we have taken the basis state, that is 0 0. So we need to perform this one. This is how the operation takes place for an quantum circuits with the CNOT gate. Okay, so here I have taken the X gate itself. We are able to represent the same thing even with the Y or Z. That doesn't matter. Okay, now let us do the first. Let us find out what is this H tensor product with I. Okay, so H means it is nothing but 1 divided by √2. 1 1 1 minus 1, that is the matrix representation of the Hadamard gate with the tensor product of the identity matrix, that is 1 0 0 1. I hope that you know how to do the operations. One more time I will show you now also. Okay, so please all the students, I request you to take a copy and please practice along with me. Okay, now in order to okay, so we are going to perform the same thing. Yes, see, this is the output of the result. So I will show you what it is. Okay, I will also write here beside it. So 1 divided by, okay, So this is 1 divided by root 2. I'm going to keep that one as it is. So here, that is the first element of the Hadamard gate, 1, going to do the tensor product with the identity matrix. So that I am going to get as 1. Then 1 tensor product with 0, that is 0. Then 1 tensor product with 1, this is 1. Then 1 tensor product with 0, this is 0. Okay, this is how we are going to perform the operation, that is a tensor product. Similarly, next one is 1 tensor product with 0, that is 0. 1 tensor product with 1, that is 1. 1 tensor product with a 0, it is 0. Again 1. This is how we are able to do the operations of the tensor product. So I hope that it's been clear to you how to do the tensor product of the Hadamard gate with the identity matrix. Okay. Now we will move further one. So now I already found out what is this one. Now I need to take the final state, that is Z0 gate, the tensor product of Hadamard gate with the identity matrix, then with the initial state function, that is 0, 0. So here, whatever we have done in the previous slide, I've kept it beside. Now let us take the C0 gate, so which have been studied in our previous session in the last class. Then we are taking the Hadamard gate. Then we are taking the initial state, that is our get 0, 0, which is nothing but our 1, 0, 0, 0. We already done all these things, that is Z0 gate and the get 0, 0, that is the tensor product of 0 with the 0. Okay. So now we need to do the performance again in order to get this result. So how to do this answer here? See, we got the answer as 0. So how to do this one, I will teach you one more time. Here see, first do the tensor product of 1 with 1, that is 1 itself. 1 with 0 is 0. Yes, this is the output of the same thing. Okay. So here we got the operation, that is the 4 by 4 matrix, that is the final state. Now I'm going to operate this. 1 minute. So this one with this I've done right now. So do I need to show that one by annotating, by writing that one? Please, anyone, please tell me.
Participants can tell that whether Dr. Kiran should demonstrate this. So some people are saying no. So I think you can continue further. Dr. Krishna Kumar is saying yes. So you can take a call on it.
Yeah. Okay. So I will show one more time. Okay, I will write here. Okay. So here we are going to do the operations. That is 1 minute. Okay. So we are going to take. Okay. So 1 divided by root 2, it will be as it is. Now I need to perform the normal matrix, normal multiplication. 1 into 1 will be 1. 1 into, so this is how we are going to do the operations. So 1 into 1 is 1, 0 into 0 is 0, then 0 into 0 is 0. Okay, so the matrix, what we are going to get, it will be in the next slide. So I will show there itself, here itself. Okay, so this is what the operation is. And I'm going to operate again on the state here, that is the initial state. So the initial state outcome will be 1 divided by root 2, 1, 0, 0, 1. Okay, so 1 into 1 will be 1, plus 0 into 0 is 0, plus 1 into 0 is 0, plus 0 into 0 is 0. So after adding all the things, we are going to get as 1. Then 0 into 1, I'm going to do this one. Okay, so I will show here. Okay, so that is 1 divided by root 2. 1 into 1, 1 into 1, that is 1, plus 0 into 0 is 0, plus 1 into 0 is 0, plus 0 into 0 is 0. Then 0 into 1 is 0, plus 1 into 0 is 0, plus 0 into 0 is 0, plus 1 into 0 is 0. Then 0 into 1 is 0, plus 1 into 0 is 0, plus 0 into 0 is 0, minus 1 into 0 is 0. Now 1 into 1 is 1, plus 0 into 0 is 0, minus 1 into 0 is 0, plus 0 into 0 is 0. So by adding all these things, we are going to get a 4 by 1 matrix, that is 1, 0, 0, and 1. Okay. Now the interesting concept will come here. So this is what I was needed to tell you. So how the states will be entangled. Okay. Here see, here the output, whatever we got is 1 divided by root 2. Then it is 1, 0, 0, 1. So I am going to alter the same thing like this. Okay. 1 divided by root 2. And I'm going to take one of the column matrices 1, 0, 0, 0, then plus 0, 0, 0, 1. So I am decompose this state into basis states. That is 1 divided by root 2 into this we have already studied in our previous class. That is, this is nothing but our tensor product of 0 with 0 plus tensor product of 1 with 1. So this state, whatever we are going to see now, this state is called as an entangled states. Okay, or it is also called as an Bell states. So here I hope that you came to clear regarding this one. So can the matrix be still simplified now? Okay, so that is what I'm going to ask you the question. So are you able to simplify this more again and again? So that is the question. So this is the entangled states. Okay, so that is what the statement is. Okay, so somebody asked the question, cannot the matrix be still simplified? So this is the one, this is the matrix, the last matrix. Okay, now are you cleared regarding this one, whatever I've showed right now? Please, okay, yes. Now this state is called as an entangled states or Bell states. Now let us look over what is our first definition or the statement of this entangled state. Okay, so sir, can you please explain the last step? So which one you were telling? So this one, the splitting one, or which one? Bibahbari Pal. Okay.
Dr. Paul, you may unmute yourself and ask in case you want to get some clarification. Please do that.
Hello, sir.
Hello. Yeah.
Hello. You said the previous one you did. You explained us how to write it in the. I
Okay.
mean, you wrote 0, 0 plus
Yes,
1, 1.
yes. The same thing, whatever we got the result here, I'm writing the same thing by decomposing it into the basis states. Okay. So the basis state which I am going to represent, I am able to represent as 1, 0, 0, 0. Understood? And I'm going to add this with the another basis state 0, 0, 0, 1. Yes, see, if I am adding both the things, I am going to get this previous state itself, the last state itself. Okay. So I hope that you understood this one. Okay. Yeah.
Yes, sir.
Yeah. Thank you. So now, is this the expression? Yes, this is the expression for an Bell state. Yes, that's right. Yes. Thomas. Yes, that's correct. Yes, see, now we are going to look over again what is meant by an entangled state or an bell state. Okay. I unmuted, sir. Thank you. So the entangled state or the bell state is called as an entangled state is a special multi-qubit superposition state that cannot be factored into a product of the individual qubits. So by taking that example, I'm going to give you another state, another uh, superposition state which has been entangled. Please tell me whether this state is entangled or not. Please think over and please tell me whether this is entangled or not. So I will give you some time to you. Please look over the same thing and please tell me the statement requires this statement requires explanation. Okay. Yeah. Okay, sir. I will. Okay. So here in this, okay, so a lot of students are saying no, sir. Okay, so I'm going to write and I will show you the same state. Let's see, this one can be written as 1 divided by root 2. And I'm going to represent this ket 0 and ket 1 as ket 0 tensor product of ket 1 plus this ket 1 into tensor product of ket 1. Ket 1. Now, I am going to write the same expression as ket 0 plus ket 1 and I am taking out the product that is common in both the terms, that is ket 1. Here see, this is not at all an entangled state. Lot of students has given a right answer. So very good, that is. So this is, I am able to represent this, whatever the state they have been given in terms of the individual state. That is what the initial states are. So that then this state cannot be used as an entangled state. So this is what the main statement of this entangled state, or it is also called as in bell states. Okay, so that is the combination of the, even in our previous examples, I was showed you in one of the starting slides, that is xi is equal to 1 divided by root 2, that is the state h with h plus t with t. Okay, so this is what the mathematical representation of the bell states or the entangled states. Even we are able to represent the same state with even with the spin states, that is up spin with the down spins. Okay, so this is also we have discussed in our previous class. So I hope that the entangled state or the bell state has been cleared to you by performing or by taking the 2-qubit systems and by taking the addressing the C0 gate and by doing the quantum circuit with the C0 with the Adamard gate. So how to perform this expressions. So this is what the quantum entanglement is. So I hope that you have been cleared regarding this quantum entanglement. So everybody is cleared on this session or the talk of this talk. Please write an yes to it. Or if you have any questions regarding that one. Okay. So thank you for everyone. Now let us move on to the today's talk. Okay.
I suggest I suggest kindly reiterate this. I suggest kindly read. This is an important situation. Needs reiteration.
Okay, sir. Do I need to do it one more time to them? Okay, so I will explain it Okay, so I will do it one more time, the same thing. So I need to represent the same thing again. I will do it one more time. Okay, so here this state xi function 1 divided by root 2. So this is, I'm going to represent this. We already know in our yesterday class also, we have studied this one, how to represent the 0 with a 0 can also be represented as 0 with the tensor product of 0. Similarly, I'm going to represent the state 0 with 1. So which we are able to write as ket 0 tensor product with ket 1 plus ket 1 tensor product of ket 1. So in this first term and the second term, there is an common, that is the ket 1 state. So where we are able to take this one outside, that is 1 divided by root 2 ket 0 plus ket 1. So what is the common in both the terms? That is tensor product of ket 1. Tensor product of ket 1. Okay, so this is the state which is the product states. Okay, so I hope that it's been clear. So you need to practice it more and more times. You need to solve the same questions by taking, or you are able to do the same thing by taking the different basis states, whether you are going to get the entangled states or not. You need to perform that. You need to do that as an homework. So it is very important because this requires some practice. So only after you do some practice, you are able to get familiar to this one. Okay.
Excuse me, sir.
So yeah, tell me.
Sorry to disturb you.
It's okay.
Uh,
Sir. Yeah.
yeah, sir. So there is a very simple question. The way you have taken psi f as C naught H means that Hadamard gate tensor
Okay.
product is
Yeah.
identity matrix and close the bracket and psi I.
Yeah, right.
Sir, similarly now in this case I am little bit confused with that the recent psi f which you have taken 1 by
Yes.
root 2 into the bracket the cat brackets. So
Yes.
sir, what is the previous step for this with psi I?
1 minute. Please ask the last line. You ask it one
Yeah,
more
yeah.
time.
So the way you had given us
Yes. So this
means
is
you
the
have,
state
yeah.
what we got it for. So if I take the state with the initial what we are going the basis states here, right? 0,
Hmm.
0. Then only
Yeah.
we are going to get the entangled state. Okay.
Okay.
Suppose if I take some other basis states, here I have taken an example in order to ask you whether the
Okay.
state, whatever we are going to get, that is 1 minute. This is
Yeah.
0, 1 and 1, 1. Here I have taken 0 and 1 as the basis states. Okay.
Yes.
So understood? Then only we are going to get this type of states. This is not an entangled state.
Okay.
Okay, understood that one. Please practice this one again. This is I understood this one. It is bit difficult to you to get understand. Just by changing the basis states, please take some other states. We are having 0, 0, 0, 1, 1, 0, 1, 1. Please
So,
try to,
excuse me, sir.
yeah.
Yeah. So in that case, suppose we take this one, the what is that? Target control as say 0 and target as 1.
1.
Then what would be the psi f for that particular case?
So psi f will be not the entangled state. It will be not the entangled state.
No, I mean, sir, the equation. Sorry to interrupt. Yeah.
It's okay. It's okay. So we need to take this first as the 0 state. Then we need to take that as an 1 state. Then we need to perform the same operations. The same operations. Then,
Okay.
so we are going to get that this state, whatever going to get, that is at the last. Okay. So 1 minute. I will show you here. The initial state for your telling for 0, 1, right?
Yeah, sir.
So 0, 1, what will be the basis states here? It will be 0, 1, 0, 0, right? We need to perform this operation. So
Okay,
then
sir,
we
yeah,
will
okay.
come to know that whether it is an entangled state or not. Okay.
So that is our psi I basis state.
Yes, yes, yes.
Okay, sir. Yes, sir.
Initial
Now it is
state,
clear, sir. Thank you.
initial state. This is initial states.
Yeah, sir. That's what, sir.
So yeah, understood.
Thank
So
you, sir.
that
Yeah, sir.
you can take 0, 0 or 0, 1 or 1, 0 or 1, 1. Okay.
Yes, sir. Yes, sir. We need to
Understood.
practice this.
Yes,
Thank
you
sir.
need to
Yeah.
practice it. So please
Yeah.
take this one as an homework. Please do
Yes,
it
sir.
for different initial states. Okay.
Sure.
Then check whether it is an entangled state, for which combination it is coming entangled state, or for which it
And
is
not,
not
yeah.
coming the
Yes, sir. Sure,
product
sir.
states. Okay.
Yes, sir.
So I hope
Thank you,
that
sir.
it's been cleared. Okay.
Yes, sir.
Yeah.
Yes, sir.
Yeah. Okay. Okay. Yeah. So it's been what the quantum entanglement means, or the entangled state, or the Bell state means. Please get some practice to it. So I hope that it's been cleared. Only one state I've taken and I've showed you, since there is a time constraint. So please practice it. If you have any doubts, you can contact through the so if ket1, so the problem on H gate, ket1 on the H gate. Okay. So ket1 on the H gate means we are going to get, we need to do that, and we need to look over into that one. Okay. So that is the Venkatesh. Okay. Yeah. So this is the operation, Sanjay. So just now I showed you, if the very simple trick for that one. You see, okay, I will send you the written material also. Okay. So you see, in this state, whatever we have got at the last, that entangled state. Okay. Here, see, very simply, you can look over into this one. If the second qubit and the second qubit of both the states, if it is having common, then that is not an entangled state. Very simple. Okay. If it is not the same, different pairs, then it is an entangled state, because we are not able to take out the common, right? I hope that it's been clear to you, Sanjay. Please practice it. Once you get the practice on that one, so you are able to get what is the entangled state and the entangled state, whether it is entangled or not states. Okay, not entangled states. Okay. Okay, then I will move on to the today's session. Okay. So I hope that it's been cleared of the quantum entanglement. So today's session is again the starting from the superposition states, so which has been discussed in our session 1 by Jyoti ma'am. Qubits, which has been discussed from classical transformation to the quantum transformation by introducing the Dirac notations, Ket and Bra, and also the column matrix and the row matrix and all. And they also showed the respective gates in the qubit states, and also the super qubits. So by Jyoti ma'am again showed how to create an superposition by using a beam splitter, and by using the Stern-Gerlach experiment, the another superposition we are able to create. So it was taught by the Dr. Rajiv Tyagi sir. Then the quantum cryptography, so which is one of the most very interesting concept under the quantum computation, which was being taught by the Abha madam. And quantum gates, so in the 6th session, so that was where ma'am has showed you the single qubit states, that is Pauli X, Pauli Y, Pauli Z, and the Adamard gates, how to represent through the quantum composers, what is the probability, what is the phase of the same states by the Dr. Vandana ma'am. So in the yesterday's sessions, we are talked regarding what is meant by quantum entanglement. So how to what is the definition by some of the classical and the quantum both the regime by taking the examples, and we have discussed the definition of an quantum entanglement. In today's class, we have completed that one by showing whether the state is an entangled state or an non-entangled states. Okay, so please do that as an homework. Okay, so feel free to ask in the group also. I will share you the notes also for the same thing. I will do the notes and I will give you for different states also. Okay, now in today's class, we are going to come up with the another very interesting concept in today's class, that is quantum teleportation. Okay, so in this quantum teleportation, so we are going to talk regarding few things. The outline of this today's sessions will be quantum teleportation and what is the history of transforming the messages, the information, even from our ancient times, what we are going to do that one. We are going to see that also. And there are teleportation means there are lot of science fiction movies are there. You have been seen in the Marvel movies or in the Star Treks. So we will look into that also. And we will come to the definition of an quantum teleportation, what it is telling in the quantum nature. Okay, so in the science. Then we are going to study what is the quantum circuit for the teleportation. That is very, very important. We are going to do that one. So by taking the quantum entanglement, whatever we have done the Bell states or the entangled states, we will take the concept of that one and we will implement it in the quantum teleportation. Okay, so we will do that one. So we are also going to do by using this quantum circuit, the mathematical approach on recovering there is an one of the very good interesting stories there between the Alice and Bob. We are going to take the same thing and we are going to recover that message through the teleportation through by using the quantum circuit. We are going to do that also. And what is the applications, and followed by the summary and question and answers. Okay, now so even from the ancient times, we are going to send the messages in different ways. So in earlier days, they were doing with the smoke signals. They were putting large amount of smoke so that foam, whatever it's coming, they were going to look at long distances. Okay, so that is the oldest form. The ancient times in the ancient China, they were doing that one. Okay, and later on, in order to send the messages through the pigeon, so they were writing and they were putting inside the box or a tiny glass, or they were wrapping it with a thread to the leg of an pigeon. They were sending the messages even through the battlefield. So during that time also they were sending it. And they even in the 16th century, the British military persons, they were putting the informations or the messages inside the water bottle and they were throwing it on the water. So in the oceans, they were doing that also. So after that, the telegrams has been came. So we are able to send the telegrams. So through the messages, and the Pony Expresses came. So where it was serviced as an fast mail delivery services, that was also came. Then telephones has been came after the Alexander Graham Bell discovered it, where we are able to communicate with each other even with far away distances. Then fax machines was came. So where the Xerox copier was introduced. Okay, so then pagers were came through in order to send the messages. Then cell phones were came, which is a wireless one. So then so instant messages, what we are going to see in day to day. So we are using the text messages with the encrypted signals and all. So we are able to see these ones in day to day. Okay, so this is how the informations has been carried away even from our ancient days. So due to the theory what we have been came up with in our 20th century, that is the quantum physics, we have got the quantum computation and all this advanced technology in our 21st century also, we are going to express all these things. Okay, now So I'm going to show you one small 30 seconds movie of the what exactly the teleportation means. So please look over into this. Okay, so these are some of the science fiction magics or the movies which have been shown in your movies or in some web series and all. So in terms of, okay, so we'll move on to the next slide. Okay, so in this, in quantum physics or in quantum computation, in the respect to the science stream, we are not going to transfer an human being from one place to another place or from one space to the outer space. So whatever you showed in this video, so we are not able to do like that. Okay. So in quantum physics, teleportation conjures notation of the science fiction magics, where characters vanishes from one spot and reappear instantaneously in another. So quantum teleportation is an vastly different and equally fascinating phenomenon that defines our traditional understanding of the teleportation. So making it as an captivating concept. So we need to, hello, sir.
I just want to say that please, I want the audience to listen very carefully. This is the steepest part of the Himalayan climb. This is the steepest part of the Himalayan climb. Dr. Kiran is going to explain very well. Please pay 100% attention. We need to keep our common sense away. There is nothing like permanent common sense. The common sense has to be kept away, and listen to Dr. Kiran very carefully. He is telling something which is extremely substantial. Thank you.
Thank you, sir. Thank you. Okay. So now, this in quantum teleportation, there is no science fiction kinds of nothing like that. Okay. So it is traveling with the speed of light, exiting the speed of light. There is no concept like that. So please do not believe in any myths like that. Okay. So now we are going to start with a story. So very interesting story of that is between the Alice and Bob. The Alice needs to send the information from one place to the another place to the Bob. Okay, so we will do this one. We will show you again this one. We are going to talk this one. So quantum teleportation is what we are going to study in this class. Okay. So here, this quantum teleportation means first thing we need to come out of our mind, that is, this is not a science fiction. Okay, that is not a science fiction. Here, this teleportation, we are able to divide that into two different words. This has been come from the Greek representations. Okay, tele and portation or portare. Tele means far away. Portation means to carry. So in order to carry an information from far away from one place to the another place. Okay. So what are the restrictions of this quantum teleportation? That is also very important. Okay. So that is no actual particles or things are moved. There is no concept like that. Second one, there is no traveling forward or backward in time. It's not possible. Moving matter from one point to the another via dematerialization. That is, means destroy a matter or a human being in that position, and in order to carry the same human being to some other position, it's not possible. We are not going to do like that in the quantum teleportation. And traveling faster than the speed of light, that is also not possible. So this violates all our science. Okay, it is not possible at all. Okay. Now, so what is meant by this quantum teleportation? First, we will look over into the definition. Then we will come to the what is that definition means. Okay, quantum teleportation enables the transfer of qubits, which we have already studied even from our session 2 itself. Okay, already we have been studied that one, while perfectly preserving the state information, allows for transmission over a great distances, think from Earth to space or even far away, by using the power of the quantum entanglement. Very, very important, this one, quantum entanglement. And from Earth to space, any faraway distance, we are able to transport our message, okay, through this quantum teleportation case. Okay, so this is what the definition of this quantum teleportation. We will get understand each and everything, so no need to get worried too much into this one. Just understand. So we are going to transfer the information from one place to the another place. If it is in 1 meter, or it might be some 100 kilometers, or it might be in far away distance from one space to the another space, or from one galaxy to the another galaxy, all these things are possible through this quantum teleportation. Okay. So in order to explain this quantum teleportation, now we are going to start it with an story. Please get understand this story. If you are able to get understand this story, then half of the class is finished. After that, we are going to do only the mathematical part. Okay. So there was an close friends, Alice and Bob. They were living in some city. For example, let us consider that as in Bengaluru. Okay. So they were Alice and Bob, they are going to create some bell states. Let us consider this bell state as B00. Then distribute the outcome of the bell state among each other. They are going to distribute this bell state. I am telling you one more time. Alice and Bob are two friends. Please listen very carefully. Please be attentive in this part. Okay. Alice and Bob are two friends. They are living in some city. Okay. They are going to create some bell state. That bell state is represented by the ket B00. Now they are going to distribute the outcome of this bell states among each other. So the Alice is going to keep one of the qubit. Here there are two qubits, we know already. Now she is going to take one of the qubit. I am going to represent generally as BA, and second qubit is kept by the Bob, that is going to represent it by B and B. Okay, so inside the ket notation. Now both these qubits are entangled with each other. So it's been entangled. Okay. After some years, the Bob, where they were together, the two close friends were together, this Bob will go to some other different city. Or let us consider, since we have already stated in the definition of the quantum teleportation, very far away. Let us consider this Bob has been moved from Earth to some Mars, another planet. Okay. By taking the same second qubit bell state, has been taken that also along with him while traveling. Okay. After some years, the Alice needs to send some message to the Bob. Okay. So since they were friends, she needs to send some information. That information she needs to send to the Bob. That means nobody, third person or any other person must see that one. So it has to be maintained that much secrecy. So she needs to send this qubit state from Earth to Mars without any other interface between Alice and Bob. That whatever the messages she needs to send with topmost secrecy. Okay. So it has to be maintained. So how to do that one? We will do that one by using the quantum circuit. So, okay. So we will complete this story. So what she will do to send that secrecy message? So she will do some operation of this, whatever the secret message as this is a qubit, with the another first qubit which has been entangled. Okay. So they are going to do that operations. Now, after doing these operations with this secret message, that is the ket psi, they are going to get some result. that result will be in the state of an classical bits, that is 0, 0, 0, 1, 1, 0 or 1, 1. Please be careful here. Whatever they are going to measure here, this two different qubit states, they are going to get the outcome as the classical bits. Classical bits means, already I told that restriction is they are not able to move with the speed of light. In the classical scenario, there is no case like that. It is going with the speed of light. Okay. So that also violates the restrictions. Okay. So this one. Then it is going to the through this classical bits. These are representation of the classical bits in the quantum computation. I will show you in the circuit also. Okay. This, whatever the state has been reached, this qubit to the Bob is going to put some operations by using this second qubit Bell state, that is this one, and is going to get the initial secrecy message which has been sent by the Alice. This is the story. Okay. So if you are able to understand this story, it is very easy for the forthcoming slides. Okay. So I hope that this has been understood. Okay. Okay. So now we will take this story forward by telling what are the requirements for this quantum teleportation. Whatever we are going to say here, some 3-4 points are there. So I will show you the same thing in the next slide by using the quantum circuit for the quantum teleportation. Okay. Here see, in the first one, a qubit can be perfectly transmitted using the 3 qubits. 3 qubits is necessary. It is very important. And we require 2 classical bits. Okay. Teleportation needs 2 qubits. In the 3 qubits, we require 2 qubits. The 2 qubits has to be entangled. Okay, entangled state, it has to be there. Just now we discussed the entangled state or the Bell state. Okay. Each part has one of the entangled pair. In the story itself, I was discussed you. So whatever the Bell states or the entangled state created by the Alice and Bob, one of that one was taken by the Alice. One, it was taken by the Bob. Just now we looked over in the previous slide. Okay. So that entangled pair. Now a message qubit that will be sent from one point to the other. Even in the story I discussed, Alice needs to send a qubit, that is the secrecy message, from one point. Okay. Hello, ma'am.
Yes, could you repeat, because some of the participants are asking to repeat the previous one. So I think it will be better if you do it now so
Okay.
that they can
Yeah, yeah.
understand this
Yes.
well. Thank you so much. Thank you.
The story, right? Whatever I said, the story, that one, right?
Yes, yes, yes,
Okay.
yes.
Okay, ma'am.
I want to say one thing. I want the participants to completely throw away their standard thinking. Please concentrate 100% on what he's saying. Please concentrate. You need to be repeated because we carry our thinking hangovers. This is absolutely non-common sense. All common sense issues have to be put aside and visit fresh. The mind has to be very fresh and totally concentrated to get issues on this. This is the crux of the matter, the heart of the matter. इसको समझने के लिए आपको बहुत विचार करना पड़ेगा, आपकी कंसंट्रेशन बहुत ज्यादा रहनी पड़ेगी, तभी आपको ये ध्यान में आएगा. पहले आपके जो पहले विचार है ये उसको सब हटा के आप सोचिए, ये हो जाएगा. You will understand down the point. We are not talking about science fiction. We are not talking about imagination. We are talking about truth. Truth. जो सत्य है उसी को बताया जा रहा है. आप सभी मेरा सभी लोगों का अनुरोध है कि वो पूरे कंसंट्रेशन से इनको सुने, तभी आपको ध्यान में आएगा. थैंक यू.
Yeah, thank you, sir. Thank you. So please, all the students and all who have been listening, please concentrate. Please think over. Please remove all other things from your brain or from your mind. Please concentrate. I will tell you the story one more time to you. Okay. Here, see, the Alice and Bob, these two are very close friends, and they are Okay, sir. Yeah, yeah, tell me, sir. Hello.
Ah.
Yeah, hello, sir. Shall I continue?
Yes,
Yes,
please
continue.
continue.
Okay,
Yeah.
okay, sir. Okay, yeah,
Please continue.
okay. Thank you, sir. Okay, so I'm going to tell a story which is very, very helpful for our next slides, or in order to get understand the quantum teleportation. So, which is basically based on the uh, real fact. Okay, Alice and Bob, these are two friends. They live together. So, in some city, let us consider that city as a New Delhi. Okay. Now, Alice and Bob, they are going to create a bell state by performing some operations, which I have already told you by using the C0 gate and the Adamard gate. They will do that. Okay. So, no need to get worried. So, they are going to get that bell state. I am going to represent this bell state as B00. Okay. Because there are two bits will be there here. Okay. One is control bit, one is target bit. It will be having 2 bits. Okay. Let it be. Now, then distribute the outcome of the bell states among each other. Okay. So, Alice is going to take one of the bell states, one of the bell state, that is bell A. Okay. So, whatever they have been done this entangled state, in that one of the states she has been taken out, and the remaining one, the second qubit, is kept by the Bob. Is kept by the Bob. Both these qubits will be in the entangled state itself, entangled with each other. I hope that you have been cleared up to now. So if it is yes, please write in a chat or thumbs up in the group, in the chat messages. Clear? Yes, yes. Thank you. Thank you very much. Okay. Now we are going forward with the story. That is, now after some years, where there have been two close friends, where they have been present in the New Delhi, with by keeping some one of the bell state and another bell state. Bob will move from one place to the another place. He might go to some other city, to Mumbai, or some other country, or some other planets also. It doesn't matter. The distance will never come to the picture here. It might be at any far away distances. And while going, he will take that state, that qubit state, that is B, bell state B, okay, second qubit state. Now, after some years, Alice, since there were two close friends, she needs to send an message. That message is encrypted, okay? So, that message has to be seen only by the Bob. It has to be no any third person in that, in between those two, Alice and Bob, okay? So we are able to do that one by using the quantum teleportation. What she will do, this state Xi, whatever the information she needs to send, she is going to do some operation. I will tell you what is that operation later. Operation with the first qubit state. Okay, whatever she has been taken, that she is going to do that qubit state. After that, she is going to get some results. That results will be nothing but our classical bits. Classical bits. Please get understand this one. They are been transforming from qubits to the classical bits, quantum bits to the classical bits after performing the experiment. Okay, after performing the operations. This, it might be B1, small b1 and small b2. This one might be small b1 and b2. I will write here. 1 minute. This is b1, small b1, and this another two lines, whichever horizontally lines. This is how they are going to represent classical bits or the measurements in the quantum computers. Okay. Now, after that, it will reach the Bob, and it is in some complex kind of thing which we are not able to read at all. What he will do is, he will do that operations or mathematical operations or by doing some experiments, whatever it is, that ket psi which has been sent by the Alice, he will going to do that operation with the second qubit which has been taken care by the Bob while he is leaving. Okay. So after doing these operations, he is going to get the initial message which has been sent by the Alice. So this is what the story behind the quantum teleportation or the secrecy of the message from one place to the another place. This is what we are going to concentrate on this today's class. So are you able to understand this story? So Arvind Kulkarni sir told no.
Yes, I just wanted to say that if there is difficulty, I would like people to understand that it takes time to understand, it takes time to absorb. So give yourself enough time. Do not be very hard on yourself because we are walking out of the comfort zone. This requires us to walk out of the comfort zone. Notice that the Bob and Alice will go away, but their being together is not going to go away. They were together is not going to go away, but they are going to go away. So they are not just individuals; they are deeper systems. You must understand that. To understand this, you must know that your attention should be taila dharavat. Taila dharavat means as the flow of the oil from the hole in a pot which falls on the head of the Shankara or the thing. Okay. If your attention is that keen, you will be able to get it. It is not very difficult, but you need to go out of your comfort zone. आपको comfort zone छोड़ के बाहर आना पड़ेगा. Thank
Yeah, thank you, sir. Thank you very much. So now we will go further. Lot of students has been said yes. Thank you very much for understanding it. Now, so what are the requirements for this quantum teleportation? First, I will discuss that one. Then we will move on to the quantum circuits. Okay. So a qubit can be perfectly transmitted using the 3 qubits and 2 classical bits. Okay. In that 3 qubits, 2 qubits has to be entangled, and in that 2 entangled states, 2 qubits, one has to be taken out. Okay, why is a classical system between them required? In order to transfer the information from one place to another place, we require a classical, like for example, like an optics kind of thing, or the laser beam, or we are going to send an radio signals from here to the satellite. Again, from satellite, we are going to receive the signal where we are communicating each other. That's why we require a classical system in this. So I hope that you got it. Yeah, thank you. Thank you very much. Okay. So now, and another one thing, a message qubit will be sent from one point to the another point, where the Alice was going to send that one from one place to the another place. Okay. And classical communication line between both the parties for the transmission of 2 classical bits is required. Just now I discussed, and even the Biju was also asked the same thing. Yeah, thank you for that one. Okay, now we will move further. This is the quantum circuit for teleportation of the Xi state. Okay, so this is the circuit. Okay, so this is, please look over in this circuit. There are 3 qubit states. Are you able to see that one? One is a Xi, and another 2 are 0 and 0. Okay. So I hope that you have been seeing that one. Now, okay. Here, see, I am going to write this circuit again. Please don't get worried. I'm going to write that in a separate slide. We will understand what is that circuit is going to tell. Here, see the state Xi, which is in the first line, at last it is going to get the same thing. So this is the operations which we are going to do it in today's class. Okay. So there are some mathematics are there. So I don't know whether I am able to complete that one or not in the time. Okay. So just I will introduce this quantum circuit. Okay. So this quantum circuit, I am going to write it here. See, there is an Hadamard gate, there is an C0 gate, there is also again an C0 gate, and there is an Hadamard gate. After that, they are going to do these measurements. So whatever I told you in the story, they are going to do some measurements with the state xi with the first qubit, that is BA or BB. So this is what the measurements they are going to do, that one. After that, in order to transfer from Alice to Bob, you see this first part is Alice and this second part, whatever at the bottom level, is the Bob part. Okay, so these are two different persons. They have been entangled each other. Okay, even they are very far away. Okay, this measurements, after that they need to send it through an classical bits. Okay, this is how they are going to represent in the circuits. Now I am going to write the same circuit. I am going to explain the same thing in by writing it. Okay, so I will write it. Please look over the same thing, and after that you tell me whether you have been get understood or not. Okay, up to that one. Okay, so now here I am going to take is okay. So why it's coming? Okay, 1 minute. Okay, here see, here I am going to take a line. So I am giving it to the Hadamard gate. This is Hadamard gate. Okay, just now we have seen this one in our quantum circuit of the C0 gate. I am going to give the initial basis state as ket 0 with ket 0. Then I am going to, this Hadamard gate is going to operate with the C0 gate. This is what the representation of. After that, it is going to get an entangled state, that is P0, 0. This is what I've told you in the story also. I am taking the same notations. Okay. After that, I am going to transfer one of the bit to the Alice, one of the bit to the Bob. Okay. Here see, I am going to transfer one of the bit, that is state BA to Alice, and another bit to Bob, that is BB. Okay, I hope that you understand up to here. So if it is yes, please. Yes, okay, thank you. Thank you, thank you. Yeah. Now, okay. Now, Alice is going to give some state, that is the hidden state. She needs to send a message or an information in a secret or encrypted way. Okay. So here she is going to give that one by taking another state to the, here see, there is one state already. There is another qubit state also here. Please be careful. Okay. Now they are going to give it to the C0 gate. Okay. Then outcome of this result, after doing the operation of this ket xi with ket BA, I've told you in the story. Okay. By using this C0 gate, after doing this operation, so they are going to give it after that C0 gate operation to the Hadamard gate. Okay. So after performing the operation with the Hadamard gate, after this output, they are going to do the measurements. They are going to do some measurements. So this measurements outcome, here also they are going to do the measurements by Alice after this state xi with ket BA. Now we are going to get that as some results will come as an output. Let this be bit B1, which is the classical information. Here also they are going to get another classical information, classical bits, that is B2. Okay. So this one, they are going to send it to the very far away, that is his friend, that is Bob. Okay. And this Bob is going to perform some operation. Okay. I'm going to change the color of the pen. So let it be very clear. This is for Bob. This is for Bob. Bob. Bottom part, whatever it is there, it is for Bob. Above part, whatever it is there, it is for Alice. Okay. So here again, here is going to do the operation with this bits, whatever she got, that one, that is Xi. And by doing the operation with this one, and at last he is going to get the information or the message which has been sent by the Alice. So this is the circuit what we are going to discuss. Okay. So I hope that it's been bit clear to you. If anybody is having, yes sir, Adamart gate, H gate. Yes, correct. Spooky action at a distance comes into effect here. Yes, yes, yes. Hanuman jumps across the ocean. Yes, yes, correct. Yes, sir. Okay. Yeah, thank you. Here, whatever we are going to do is the operations. Okay. So it's been time's up to me. Okay. So this is what I'm going to say that one. Yes, it's the only entangled state could only decrypt the message. Exactly right. Exactly right. Yes, correct. Correct, correct. That's what we have studied in our previous sessions and today also. So if you have any questions up to now, you can ask me here itself. It's received fast.
How the message will be extracted?
Okay. That is the next upcoming slide, sir. Next upcoming slide is based on that itself. Okay, Yogi Kulkarni. Yeah. Tell me, sir. Yogi.
Yes, sir. If we have to send the message with classical bits, then we also have quantum encryption. Why we need this entangled state?
Means in order to keep the secret of the message, to maintain the secrecy, we require that one. So even without knowing anything, whatever the state what she was given, she will never be knowing what she has been given. Like that, it will be get encrypted. That is what going to say in the next one. Okay, that's what I'm going to show you the same thing in the next slides. Okay, how does Bob know that message has been received after the performing the operation of the original message? I'm going to show you the same thing. Okay, so I will go into why only 3 qubits? That is what the operations. That is how the quantum teleportation will takes place. Means in order to create a quantum entanglement, we require 2 qubit systems. For the quantum teleportation, we require 3 qubits. Means 2 qubits for entangled, 1 qubit is for to transfer the information, whatever the encrypted message, whatever the very highly classified message we require. So we require for that one. That's why we require 3 qubits.
Why the 2 lines are needed? You draw on 2 lines. Why 2 lines?
Here, sir, which is in the pink color.
Why 2 lines are needed? You have drawn 2 straight lines.
So which one here? This is the one you are talking.
Yes.
I will show you that one.
B1,
This is the one.
B1, B2. This 2 lines.
This 2 lines is the representation of a classical thing in the representation, the quantum computation, sir. So because they need to distinguish between the quantum to the classical, that's why the representation is shown like this for our understanding.
It takes the help of classical communication line.
Yes, exactly right. This has been proved results. In 2017, they have been done by the Austrian scientist, so Zeilinger. So he transported it for 143 kilometers. He has been done. Even in the China, they have been transmitted it for 1,400 kilometers. Quantum teleportation has been done. So that is, they proved these results. Yes, it's there.
Hello.
Okay. Yeah. Tell me, sir.
Hello.
Okay. Now I'm going to show you this the same states by doing little bit more things here. I'm going to come back to the original thing. Okay. So here mainly there is an state which has already showed you. This is the circuit. I have written the same thing here also. Okay. Now here I'm going to perform the operations one by one. Okay. First, I will do what is the tensor product of ket0 with ket0. I am going to represent it by a state called ket state omega 1. Whatever the result we got it, I am going to apply it to the Hadamard gate. After making the operation with the Hadamard gate, we are going to get some state that is represented by ket omega 2. After making these operations, whatever the mathematical operations are there, after that we are going to apply it for the C0 gate. After this, we are going to get the entangled states. Entangled states will come here. One will be going to here, the entangled states. I am going to perform this Bell states or the entangled state with the Alice Xi. Whatever the message she needs to send, we are going to perform that one. And I'm going to represent that state by Xi4. After that Xi4, again, I am going to send it to the C0 gate. Here, see, already here, entangled state is there. Already she is giving some other qubit state. After performing with this C0 gate, it is going to give some other information. She only will be not knowing what she has been sent. Like that, it is going to get happen. Okay. So nobody will able to see anything in the between at all. Nobody can decrypt it. Okay. I'll show you even in the mathematical part also the same thing. Okay. Again, state Xi5 will come. Whatever the operations are there, we are going to get it on the Hadamard gate. Again, this has been going to give some other different qubits and all. 3 qubits will get again. We need to decrypt again that one by doing some measurements. After that, at last, we are going to get the original message which has been given by the Alice. Okay, so whatever the Alice has given here, Xi, we are going to get the same thing. Okay, one by one, we will do it within next 5 minutes. Okay, so I hope that it's not been getting late. Sorry for taking your time. Okay, so this is the first state. I am going to take it. Okay, I am going to perform the operation that is state Xi1. Here see Xi2 and Xi3. This is the first I am going to take it. So Xi1 can be represented as the tensor product of 0 with 0. I hope that it's been understood. The first state, everyone. Yes, you can use the 1-1 state also. Yes, you can use it. No problem with that one. So take that as a no mark. Yes. Okay. Now I'm going to take the Hadamard gate acting on the state Xi1. Okay. So for state Xi1, I'm going to write this one here. So whatever it is there, I'm going to write again. I will show you. So please, you also make practice of these things. Okay. Okay. So you see, we know that H acting on ket 0, we are going to get an output as 1 divided by root 2 ket 0 plus ket 1, which is in the superposition states. Now here, this is going to act upon a state called ket 0. Here see, the same thing is acting on this one. So what is going to get an output ket root 2? That is ket 0 dotted with ket 0. That is ket 0 into 0 plus ket 1 into 0. That is what the operation is taking place. So this is the tensor product. Okay, this is ket 0 tensor product of ket 0. So it has become the state, entangled states. Okay, so this has become, it's not an entangled state, it's a superposition states. Okay, so because, okay, it's a superposition state. I hope that this is clear to you all. Yes, okay, right. Now, whatever the outcome of this Xi2, that is omega 2, I am going to apply it on an C0 gate. Okay, so now we are going to apply it on a C0 gate. Here, see, so C0 gate, if I am going to apply it, we are going to get an 1 0. So what does the C0 gate says? So if it is having 0 in the control qubit, so if it is having in the 0, it is going to get an 1 1 state. So that is what we have discussed in the previous class also. Okay, so this is nothing but our entangled state. Today also we have done in this one. This is what the entangled state. Here the output we are going to get as B00. Okay, so this is the first part of the same thing. Okay, now whatever we have got it, we are going to distribute this entangled pair of the qubits to Alice and Bob. That is what the story says. We are going to do the same way. Okay, so this is what the state Xi. This is B00. Okay, so okay, here see, one of the state we are going to give it B00 to the Alice and also to the Bob. So this is omega 3, which we have taken it from the previous slide. Now I am going to apply that ket Xi on this entangled state. Okay, so ket Xi is given by the some superposition states. She is going to give in that state as a message. Alpha ket 0 plus beta ket 1 is acting on the entangled state. Now this is the result what we are going to get. Here see, this ket 0 is acting on ket 111. 1 by root 2 is a constant. We have taken it outside. Where alpha is a probability, we are going to take that also. 1 divided by root 2, alpha ket 000 plus alpha, making an operation on ket 11, alpha 011 plus beta, that is the second superposition, that is beta, that is 100 plus beta 111. This is the output of the omega 4. That is that state, that qubit state. Okay, so here see, whatever she has been given already, it has been she is not able to see what is that state at all. Here see, it is coming in the 3 qubit states. So she only do not know what she has been given to her. Means nobody can decrypt in the between. It's not possible at all to do that one. Okay, so here, okay, now Alice apply C0 to our qubits. So we require this one, this information. That is, if I am having a control qubit as 0, it is going to get the same thing. If not, if it is having 1, we are going to get the swap of that one, which has been discussed in the previous class. I am not going to discuss too much on that one. So time is running up. Okay. Sir, can I take some 5 minutes more or shall I stop? Ma'am?
You can, sir.
Okay, sir. Thank you very much. Okay, so now whatever the state which have been got in the Xi4, I am applying it on the C0. Okay, so you see C0 acting on omega 4. C0 we already know, so that is 1. Okay, what it is going to do here, see, in this 0th state, 0, this is the first control qubit, this is the target qubit. Means there is no change in the outcome of the result in the C0 gate. It is the same thing, there is no change. Again, there is 0 in the control qubit, there is no change at all. So I am going to write the same thing, 0, 1, 1. Here see, please look over here. Here the controlled qubit is 1. That means I need to change from 0 state to the 1 state after applying it on the C0. Here see, I'm going to write it on 1, 1, 0 plus beta. Here it is having in controlled qubit as 1 and this is having a target qubit as 1. I need to swap this one, that will become 1, 0, 1. Here see, already the information has been changing from one gate to the another gate. It is going on changing it, the informations. Okay. Now, so I hope that it's been cleared up to here. I will move further. Okay. So we got Xi-Fi here. Apply this get Xi-Fi to the Hadamard gate. Okay. So we are going to get the Xi6. Here the last operation, it's bit lengthy one. Please look over very carefully. Here see, C0 gate acted on the Xi4 that we got in the previous whatever we have got. We have taken the same thing. Now Hadamard gate is acting on this get Xi, omega 5. Okay. So Hadamard gate, it's acting on an 1 divided by root 2 and the same representation I have splitted in terms of ket 0 and ket 0, 0. Okay. So for our easier calculations, we have performed like this. Because why I'm did like this means Hadamard gate now will act on ket 0 and Hadamard gate will act on ket 1. That is going to get the result as ket 0 plus ket 1 divided by root 2. Here ket 0 minus ket 1 divided by root 2. That's why on acting on this ket 0, we are going to get like this. Okay, so the same thing I am going to show here in the next points. Okay, you see 1 divided by root 2, I have taken out the common. Hadamard gate acting on alpha ket 0. Alpha I have taken outside. Hadamard gate acting on 0 state. We are going to get ket 0 plus ket 1 divided by root 2 and ket 0, 0 plus alpha Hadamard gate acting on ket 0, that is ket 0 plus ket 1 divided by root 2, ket 1, 1 plus beta. So Hadamard gate acting on ket 1. Ket 1 means ket 0 minus ket 1 divided by root 2. And again, it is this is the basis state 1, 0 plus beta as it is I have written. Hadamard gate acting on ket 1, that is ket 0 minus ket 1 divided by root 2 into ket 0, 1. Okay, now I will simplify this one furthermore. Here see, 1 divided by root 2 and each and every terms there is an in the denominator there is an root 2. If I take it out outside, we are going to get as an 1 by 2. I hope that it's understood. Now I am going to perform ket 0 with the 0, 0. Here see alpha. This is ket 0 with 0, 0. Alpha I have written as it is. Ket 0 with 0, 0. We are going to get the 3 qubit states. Okay. Plus alpha 1, 0, 0. Plus alpha this part. This is the first part. This is the first part. This is the second term. Alpha ket 0 with 1, 1 plus alpha 1, 1, 1. Then in the fourth term, beta ket 0, 1, 0 minus beta 1, 1, 0, 1, 1, 0 plus beta 0, 0, 1 minus beta 1, 0, 0. Here see, there is a transformation of the states as well as the phase also. Phase transformation also showing by taking the negative sign. Okay. So after this, what I am going to do is I am going to take out the common terms. Common terms means here common qubits. I am able to take that one outside. I will show you 1 minute. Okay, you see there is an ket 0, 0 is common here, and somewhere here in the which term? Okay, here ket 0, 0 it is there. We are able to take out that common. Okay, so the remaining part will be alpha ket 0 plus beta ket 1. Next, in this, I am taking in common of 1, 0. And where is 1, 0 here? Here at last. Okay, so here ket 1, 0, that is alpha acting on ket 0 minus beta acting on ket 1. Okay, that is the remaining terms. Next, the another one is here in this term, we are going to take 0, 1 as the common with here. Here we are able to see. So plus 0, 1. The remaining term is alpha ket 1 plus beta ket 0. Again, after that, ket plus 1, 1, 1. And the last one is this one. Plus 1, 1. The remaining term will be alpha ket 1 minus beta ket 0. So here we have performed an operation in such that we are going to get an classical states. Are you able to observe this one? Observe this classical state. This is an quantum qubits, but the same thing, after this measurement, I am going to give the measurement, right? After that, this is going to act as an Alice measurement is going to act as an classical bits, that is 0, 0, 1, 0, 0, 1, 1, 1. With respect to that, there is some information, there is some measurements. You are able to see these measurements. Okay, this is the measurements. Okay, so the same thing I am going to show you. Please, this is bit practice you require. Just I am showing it. Okay, so I'm clearing this one. I'm going to the next slide. Okay, so apply which converts after the measurements. So this is what the measurement outcome is. Okay, so after this, I was written the 2 lines here, right? So that is what called as an Alice measurement, which is the classical concept of the same thing. Okay, and the resultant states, what are the resultant states are? Alpha ket 0 plus beta ket 1, alpha ket 0 minus beta ket 1, alpha ket 0 plus beta ket 0, then alpha ket 1 minus beta ket 0. This is what the resultant states we got. Now, after getting this one, Alice measurement has been made. She is going to send it. She is going to communicate it with the Bob. Now, we need to look over what are the operations he is going to do. How the Bob is going to recover the state ket xi. Here, see, in this state, in the state of this resultant state, whatever it is. So, how the operations is going to do? Here, see, the Alice was send the signal at starting state was alpha ket 0 plus beta ket 1. He does not require any informations or any gates to convert that one. There is no operation is required. So Bob is getting, this is the Bob case. He is recovering the state. He has already got the information. He has got already the information, but it is in the 4 different states. That is important, another thing. Okay. Now, this is having an resultant state with the minus. So I need to transfer this minus sign phase transformation by using an operator called as an Z operator or Z gate. Okay. So Z gate is represented as, I know that you will be knowing this 1, 0, 0 minus 1. Acting on this state, Bob state, that is resultant state, we are going to get as alpha ket 0 plus beta ket 1. Are you able to get this? How is recovering? By applying the Z gate. After that, this is alpha ket 1 plus beta ket 0. Here, see, here, okay, here I need to write as plus. Okay, I made the mistake. Okay, so he needs to change this state. Plus is there is no phase transformation. He needs to swap ket 1 and ket 0. So which is the gate? That is the Z gate. That is 0, 1, 1, 0. Okay. So by applying this one, we are able to transfer this one to this states. So here, okay. So where I was doing this one. Oh, sorry. It was correct actually. It was correct. Sorry. I was explaining this one. Okay. Now there is an transformation, that is an we needed to transfer the state ket0 to ket1. So we are going to apply this another gate that is called as an X gate, which is going to swap the states from ket1 to ket0, then from ket0 to ket1 by applying through the X gate. Now there is an negative sign. I need to transform this phase. So I am going to apply the Z gate on the above operation. So again, we are going to get the alpha ket0 plus beta ket1. This is how he is going to recover the this one from the basis state, that is ket whatever the Alice was sent the information in terms of qubits, that is xi is equal to alpha ket0 plus beta ket1. He is going to get the recovery. He has got all the results even at very far away distance. There is a mutual entanglement between those two things. So this is what the quantum teleportation is going to do. Okay, so this is the concept. So I hope that some of the students, I think they understood this one. I tried to explain at my best. Okay, so I could have, I think, made bit better. Okay. Sir, this is a kind of algorithm which someone has made for us to learn. Okay. Hello, sir.
Yeah.
Thank you so much, Dr. Kiran, for such a wonderful talk. You have walked us through with different, say, applications which we have gathered through the week, starting from the classical bits usage of the qubits and following by the quantum gates. In your talk, you talked about all the quantum gates, and this is a very difficult, I think, concept to understand. And as has been mentioned by Dr. Kulkarni, we have to wash away our pre-knowledge in order to gather this or capture this knowledge, which is entirely different than the ones which we actually know. And you're walking through with the help of that historical perspective, and adding that movie was amazing. It was truly captivating. And I think you have answered all the questions in between. And there are last one which I would like to read for you. There is a comment by Dr. Abha. She says classical bits are represented with 2 lines, and this was one of the applications in the quantum cryptography where entanglement is used. And E91 protocol quantum cryptography is a method that uses entangled pair of photons. So this she has written. And there is a question by Hemant Sista. Can we define beta in terms of alpha and simplify it further?
So alpha and beta are the probabilities. So you are able to change that one.
Yes. So we saw the example of the biased coin, that even we can make it even any other thing also. And in the examples by Dr. Jyoti and Dr. Raji, we talked about the probabilities of different gates. And I would like to add this, that all this entanglement and this teleportation can be implemented through IBM computer also. I showed you that the composer for IBM. So all of you, those who are interested, first try with the simple gates, and then later on you can try these concepts also basically in the IBM, and other simulators are also available. So all participants are requested to kindly go through those simulations, and they can try these ones also. There is a hand raised by Yugen Kulkarni. You may unmute and please ask your question, Yugen.
I've shared the
Sir,
yeah, tell me.
yeah.
Tell me.
Yeah, sir. Initially, yesterday's lecture, you said that suppose there is one big particle and then we get 2 particles out of it. So these particles are entangled. So I have 2 sub questions in this. So what happens if the another particle gets interacted with the third particle? Then the entangled state of the other particle will change or not? And the another sub question is, what if instead of 2 particles it is split into three different particles. Then
So-
how can we know about that?
So by interacting with another particle, so it might change its states. So we do not know whether it will change or not. We need to perform the measurements. So after that itself, we will come to know. So we are even able to take such a type of disintegration of the particles into three daughter particles and all. So we can make that one also. Yeah, it might be possible. It's there. So that is in the
So
higher state, I think. Yeah.
If the particles are interacted with some other particle, then the entanglement might be lost, no?
Yeah. So it might get lost. So only after the measurements, I think it will come to know. Based on which of the particles we are going to talk. So based on that one.
I think we will be sharing the video link and the YouTube link to all the participants. That will be done by Dr. Madhusudan. So if you have missed on anything, please catch it up with that video. And handwritten and other I think PPTs can also be shared with the passage of time. So in case something is not clear in this particular session, because you need practice on that. And sir today has shown a state 00, but it can be for other states also. It can be worked out. One can try to understand that what is the meaning of entanglement and how it is being utilized in the teleportation. So all these things can be taken care of. So Dr. Kulkarni is also raising a hand. Sir, please unmute yourself and ask. Kulkarni sir, please unmute and...
I just wanted to say that these two concepts of entanglement and teleportation.
Sir, you are not
Sir,
audible
please.
now. Please unmute yourself.
Vandana ma'am, can you give,
Yeah.
please?
So please make sure that you are not in the hangover of the Newtonian physics. Thank you.
Thank you so much for your
Vandana,
comment.
can you please give the link for the simulation that you have shown in your class? The link for simulation.
With IBM, yes, we will share that one, sir.
Yeah,
We'll
yeah.
share that.
I will share in the group again. I will share in the group. Even if you write in the Google, just write IBM quantum computer, you can get access to that. You need to register.
But in WhatsApp group, we cannot write anything. There is no, we are not allowed to write anything.
Please send us an email, because that access will be given soon. So please send us an email in case we are answering all emails.
What is email
So
ID?
please,
I don't know the email.
this is given in the poster also. That has been given in the poster. I will share the poster again. And
Okay.
any query, we are answering to all the queries being asked in the through the email.
Okay.
Dr. Kiran, there is I think it is written in the chat that the quiz link is not getting opened. So can you just look into that?
Ma'am, just I opened it. It's been opening. I don't know why. Okay. I will try one more time.
If somebody has written that it is open for me, it means if one person is able to open, it will open for all. So please, I think it is getting opened. Please do that.
It's open.
Someone is writing opening, someone is writing not opening. So thank you for sharing the link of the IBM computer. Thank you so much. I was about to do that in the in the chat. Yeah. Thank you.
Thank you. Thank you.
So I think majority of the questions have been answered by you. If still anyone has got any doubt, they can ask by asking or unmuting your mics. And otherwise, I will hand over. I will again thanking Dr. Kiran. I will hand it over back to Dr. Madhusudan. Thank you so much for the wonderful talk.
Thank you,
you
ma'am.
very much.
Thank you very much.
And making this topic so difficult topic a simpler one. Thank you so
Okay.
much.
Thank you, ma'am.
Uh, Thank you, Dr. Kiran, for the wonderful session on quantum teleportation. I also thank Vandana ma'am for your skillful hosting of today's proceeding. We are already running late, so without talking much, I would like to end the session. I thank one and all for your active participation. See you tomorrow on the 9th session. Meanwhile, we kept on reminding you about the completion of quizzes and assignments. I hope you are aware of that. So please try to complete today's quiz also. We enter the 9th day tomorrow, so that we'll be having less time. So try to complete all the quizzes shared till today. With these few words, I'm ending the session. Good night. See you tomorrow.
Yeah.
Thank you so
Good night,
much.
everyone.
Thank you. Good night, everyone. See you tomorrow. Bye-bye.